So in this last video, we're going to introduce the definition of big O and talk about how that definition lines up with a lot of the things we've wanted from asymptotic analysis, which is we care about large sizes of n, and we don't care necessarily about constants. So we'll see how that definition of big O kind of plays into those things we wanted out of our analysis. So in this part of the video, we're really going to be focusing on mathematical definitions. And these mathematical definitions will be formal and rigorous. If you're analyzing simple or familiar functions, don't bother with the formal definition. If you are comfortable using your intuition to analyze something, you should definitely use your intuition. In this part of, for this video, we want to introduce these more formal tools, because in the future of this course, we're going to be analyzing a lot more subtle big O statements. And we need these mathematical definitions to know exactly where we are. And so we're going to teach you this formal definition. So if you come along weird edge cases, you know how to approach it, how to tackle it. You can always go back to the definition. And this really goes to our second goal, which is that mathematical rigor. So big O definition. I mentioned that this definition of big O kind of matches our intuition for what we're doing in asymptotic analysis, where we care what happens as n gets large, and we don't really care about constant factors. These two facts make big O the right tool for our analysis. Big O is actually something from the math people, but we stole it because it's so useful for our analysis. Maybe I should say borrowed instead of stole. So I'm going to show you the definition real quick. It's weird at first, the first time you see it. There's a lot of things there, but I promise you I'll show you the examples of why this makes sense. So here's the formal definition of something to be big O. F of n is big O of g of n if there exists some positive constants c and n0, such that for all n greater than or equal to n0, f of n is less than or equal to c times g of n. Oh my goodness. That is a mouthful. Here is the intuition for what this definition is trying to say. It's saying that g of n will eventually dominate f of n. It will eventually be larger, ignoring some scaling. Okay, there's so much to this definition. Let's try to unpack it. The key crux of this is that f of n is less than or equal to c times g of n for all n greater than n0. And so part of this definition is choosing what's my constant c and what's my constant n0. So why does this definition need an n0 in it? Why don't we just say this is true for all n? Well, when we want to analyze functions, it's not always clear what their behavior is when n is small. It might not be that you start seeing differences, or you see one dominating the other, until n gets really, really large. And so this statement, for all n greater than or equal to n0, we're saying at some point, this second function will start dominating the other one and will be bigger for all of the remaining n, for all n greater than n0. And so this n0 is trying to identify, hey, they might be smaller, they might go up and down before this point, but after this point, the second function is bigger. So that's why we need that n0. And then the second part of this definition, it requires that constant c. So why might we need a constant c here? So take, for example, these two functions. F of n is equal to 5n, and g of n is equal to n. So from our intuition that we saw from all this past lecture, you would probably say, oh, you just higher order term, drop constants, 5n is O of n. But g of n right now, as it is, will never dominate f of n, because 5n is greater than n. So this is why we allow constant scaling. We allow us to scale the second function g so that we don't worry about these small constants that might be present in the function. It allows us to say that 5n grows like n, but we ignore that constant, the 5 in that, because we're trying to get at how is it growing. So what this definition is getting at is that g of n eventually dominates f of n. And I should put a little asterisk there. It's not just g of n, it's a scaled version of g of n by some constant factor. Okay. So the definition was weird. It gets a little bit weirder when you think about trying to prove that a function f is big O of g. I still want us to do an exercise with this because I think it will be useful. But I want to highlight, in the learning objectives I highlighted in the very first video for today, I did not say I want you to be able to do one of these proofs from scratch. So it's okay if this next bit is a little confusing. I want to show you how you go about thinking about attacking one of these problems. Okay? So here's our goal. We want to prove that and this is just an example, I've just made up these numbers. We have some function that's equal to 10n plus 15. And I want to prove that that's big O of n. So in order to do this proof, I need to pick a constant c and n0 such that this definition on the top right, f of n is less than or equal to c times g of n, is true for all n greater than n0. So my proof is essentially just to show I need to pick two constants and show that f is less than n, the scaled version of n. And so one common technique for doing these proofs that I'm going to show you here is you apply the definition term by term to gather some true statements, and then combine those truths for your overall proof. So here's what I mean by this. This f function has two terms, 10n and 15. We'll tackle each term individually at first. So 10n is going to be less than or equal to c times n. When is that true? For what c and which values of n? Well, that's true if c is equal to 10, and it's true for all n. And so we came up with this essentially useless statement. 10n is less than or equal to 10n for all n. That's a true statement. They're definitely equal, so they are also less than or equal. Okay, so that's the first one. Seems like kind of a useless step, but I promise it will help us. Now look at this second one. We need to show that 15 is less than or equal to c times n. And so we need to figure out a c and an n0 that this would be true for. Well, it's definitely going to be true for c is equal to 15 and for n is greater than or equal to 1. So 15 will be less than or equal to 15n when n is greater than 1. Now, important point. There is no special reason I had to choose 15 and 1. This would also have been true if I chose c is equal to 17.4 and n is greater than or equal to 1.7. That would make that statement true. 15 is less than or equal to, I think I said 17n, when n is greater than or equal to 1.7 or whatever, right? Those statements are also true. So there's lots of flexibility here for how you choose c and n as long as you show that this less than or equal to statement holds. Okay? So now I have these two truths. Let's add them all up so we can kind of tackle the overall problem. So 10n plus 15, our original function, is going to be less than or equal to 10n plus 15n. Because I've done this for both of these subparts, this will be true for all n greater than or equal to 1. Now, why greater than or equal to 1 and not for all n? Well, that first statement about 10n, that statement was true for all n. But the second statement about 15 is less than 15n, that's only true for n greater than or equal to 1. And so this one kind of restricts the n's we have to look at for our overall statement to still be true. But since this is true for n is greater than or equal to 1, and for the 10n case, it was true for all n, it's also going to be true for when n is greater than or equal to 1. And so you can add those two up, 10n plus 15n, to get 25n. Why are we doing all of this? This seems so complex. But I promise, we just proved it. We just showed that 10n plus 15 is less than or equal to 25n for all n greater than or equal to 1. In this example, c is 25 and n0 is 1. We just found two numbers, c and n0, to show that this less than or equal to relationship holds. So we have just proven that f of n in this context is big O of n. All of that work just to show that it's big O of n. Which is why everything I showed you in the last video about find that highest order term and drop all the constants generally is a much more useful heuristic than doing this whole proof from scratch. But it's important to remember that this definition and the proof that requires it needs you to pick that n0 such that for all points afterwards, g of n is bigger than f of n, or at least g of n scaled by that constant c that you also have to choose. All we're really doing here is upper bounding f. We're finding an upper bound for f that describes its behavior. Now, one thing that's important to highlight about big O is that it doesn't necessarily have to be tight. What do I mean by that? Let's consider, is 10n squared big O of n cubed? And you might say, well, no, because the powers don't match up. But you always go back to the big O definition. It's true, it fits the definition. 10n squared is less than or equal to some constant c times n cubed. Well, when is that true and for what constants? Choose c is equal to 10 for all n greater than or equal to 1. If you pick those two constants that way, then this less than or equal to relationship holds, which means 10n squared is big O of n cubed. And so big O is just an upper bound, and it may not be tight, it may be a loose bound, so it might not actually be very accurate. So for example, all of the following statements are true. 10n squared is big O of n cubed. 10n squared is also big O of n to the fourth. 10n squared is also big O of n to the fifth, and is also big O of n to the n, and even n factorial, where n factorial is n times n minus 1 times n minus 2, etc., all the way down to 1. So big O is an upper bound. And this upper bound may or may not be useful. It might not even be close to the truth, what the true function is. And so what we'll see on Friday is thinking about other tools for asymptotic analysis that might help us get a tighter bound, one that tells us more about the function, just saying, well, it's definitely less than this humongous value. So all of this was trying to get us through talking about starting at code and getting to complexity class. And this last bit in this video, what we've shown you is that big O does have a mathematical definition. And the way the definition works is it fits all that intuition we had for dropping constants and for picking the dominating term. So as a reminder, the takeaway here is using the definition to help us gain intuition, not necessarily knowing how to do these proofs from scratch. So in the class session today, we'll get practice talking about these ideas and trying to do some of these problems to make sure that we get this intuition.